So let me start with a confession. I've been working in cosmology for 20 years, and I'm fairly disappointed by now because all the objects that we heard about are dead objects. And as far as I'm concerned, the most interesting aspects of our existence have to do with life here on Earth. And so I would like to bring a human perspective into the discussion here. And I'll try to talk about things that are sort of down to earth, not too much out there. And here is a picture of the Earth that we are standing on. It's just a piece of rock. It was molten to start with. That's why it's roughly spherical once it's solidified. And the Earth is a piece of rock orbiting the Sun, which is one out of many stars, tens of billions of stars in the Milky Way galaxy, which is one out of hundreds of billions of galaxies in the universe. But surely there was a time when stars like the Sun and galaxies like the Milky Way galaxy did not exist, since the universe was much denser than these objects early on. And so trying to understand how we came to exist relates our existence to our cosmic roots. We would like to understand the story of Genesis in scientific terms. And that's what many cosmologists are doing right now. So that's why the study of cosmology is relevant. And the current picture, we currently have a standard model of cosmology. And in this picture, as Alan described, the universe is by and large uniform, but there are small inhomogeneities in it. And early on, these were small ripples in the density of matter that grew with time due to the unstable nature of gravity. So you can think of these as waves on the surface of a pond, but regions that were slightly denser than the average density of the universe became even denser with time because of the action of gravity. So more matter was driven into these regions, and eventually they collapsed to make bound objects like the Milky Way galaxy, inside of which the gas, the ordinary matter, was able to assemble, cool, and condense to the center and make fragment into stars like the Sun. So we can follow this picture and understand how we came to exist. And in fact, we can follow it quantitatively using numerical simulations. We can start with initial conditions that match the early conditions in the universe that we can observe by looking at the cosmic microwave background. And then feed those initial conditions into a computer simulation and try and figure out whether one ends up with galaxies that look like the Milky Way galaxy. And in fact, here you see a zoom in on a simulation that was actually generated here at the Harvard-Smithsonian Center for Astrophysics. And one of the galaxies here looks just like the Milky Way galaxy with a neighbor that looks like the Andromeda galaxy. So we are able to produce on the computer conditions that look just like the universe today from initial conditions that look like the cosmic microwave background at the early times. And that's very reassuring. It tells us that the laws of physics that we're using based on what we see here on Earth apply to the universe at large. This is not to be taken lightly because it's not at all obvious that we know all the fundamental principles that control the universe, but it turns out that we do a pretty good job starting from the initial conditions and ending up in systems that look just like the Milky Way galaxy. And here is a picture of our archaeological dig. So we're here in the center. Since the Big Bang took place 14 billion years ago, we can only see out to a certain distance because light propagated that distance since the Big Bang. So there is a spherical region around us that we can actually observe. We can't see anything beyond it because light from more distant regions did not have time to reach us by now. And so this is our archaeological dig. And as we go deeper into space within that volume, we're seeing how the universe looked like at earlier times. So the farther we dig into the universe, the earlier is the layer that we are uncovering. Just like an archaeological dig, except it's spherical around us. So any direction you dig, you are supposed to see the same thing, statistically speaking. And of course, if you want to go all the way back to the Big Bang, you need to go to the distance that light traveled over 14 billion years. But you can, so far, for example, we have an image of the universe from when the universe became transparent, and that's the cosmic microwave background that comes to us from a spherical shell around us that emitted that radiation. We can also map what is happening in between us and that distant photosphere that we observe in the cosmic microwave background. And what you see here is this redshift symbol that tells you how much the universe expanded since a given cosmic time. So if you see, for example, a redshift of 1,000, that's when the universe was relatively dense, and then it expanded by a factor of 1,000 since then. And that's where the microwave background is coming to us from. Now we can take images of the universe at very early times by going very deep into space. And this is one of these deepest images. And we can see galaxies in it that existed when the universe was 500 million years old, much younger than the present age of the universe by about a factor of 20 or so. And the way to identify those distant galaxies is to look at the absorption of light by hydrogen, which actually eats up part of the emission from those galaxies. And the longer the wavelength at which this absorption takes place, the higher is the redshift from where we see the light, because the wavelength of light is being stretched by a factor that is related to how much the universe expanded since the time that this radiation was emitted. And on the computers, we can in principle feed the initial conditions of the universe and figure out the answer to the question, when did the first stars form? And the current standard model of cosmology predicts that the first stars formed about several tens of millions of years after the Big Bang. And here you can see the results of such simulations. When you follow the formation of the very first clumps of ordinary matter that end up in stars, you find that those stars were actually more massive than the sun by a factor of 10 to 100. These were relatively massive stars because matter was hot early on, and the rate by which matter assembled onto the seeds that made the stars was higher than it is today. So these were very massive stars that started the process. And we can actually, in principle, measure or observe the effects of these stars, the environmental impact that these stars had because they emitted ultraviolet radiation, and that radiation broke the hydrogen that filled up the universe into its constituent electrons and protons. And you can see this process by observing the hydrogen. Hydrogen glows in a radiation that we can observe in the radio. And what we expect to see are holes in the distribution of hydrogen due to the first galaxies that emitted the radiation that broke the hydrogen in the vicinity of those galaxies. And this kind of a map is so far only available in plots that theorists made. But this technique of trying to image hydrogen is being pursued now by several groups around the globe in trying to really see the effects of the very first stars on the rest of the universe. Most of the discussion in cosmology is focused on dead objects, stars, galaxies, without any notion of life in them. And a very interesting question is, when did life begin in the universe? And so I was wondering about this question actually just a few months ago on Thanksgiving Day. And I realized that the first stars were actually made tens of millions of years after the Big Bang. That happens to be the time when the cosmic microwave background that Bob Wilson discovered had a temperature which is just room temperature on a sunny day. So that raises the possibility that if the first stars formed around that time and planets were made in the vicinity of those stars, then these planets do not really need the heat from their parent star. They can be heated by the cosmic microwave background. And one can have liquid water on the surface of these planets. So in principle, life could have started at that time. And the cosmic microwave background would act as an incubator that allows liquid water to exist on the surface of these planets and the chemistry of life to begin at that time. That was very early in the evolution of the universe. Now, even if the conditions were not right for making planets and allowing life to exist at that early time, this is absolutely the earliest time where life was possible. And more likely, life started somewhat later. And of course, 14 billion years later, we exist. But we might be just relatively latecomers to the game. And the universe might be full of life. It's very difficult, actually, to detect evidence for life elsewhere. Last summer, I tried to estimate how far away can we see, for example, a nuclear war that a civilization on an extrasolar planet has. And it turns out that even with the best telescopes at our disposal right now, we can't really see such an event at the distances of the nearest stars. So life actually produces very minute signals that are difficult to detect with present-day instrumentation. Now, so far I discussed the past, and since my two daughters are in the audience, they care mostly about the future, and I would like to now move from the past to our future and ask, what does the future hold for our universe? That's an interesting question. Most of my colleagues do not really worry about it because they say, well, it will take a while before the universe will change. We can't do observations of the future. Therefore, let's not think about it. They're very practical people. But to me, the intellectual value of a question doesn't depend on whether we already have the data for it or not. So I actually am very curious to figure out what happens in the future. And shortly after the discovery of the accelerated expansion of the universe, it occurred to me that, in fact, if we sit right here, and this is either us or the US, looking outward, we would see distant galaxies moving away from us, but their speed is increasing with time. And so if you wait long enough, eventually a distant galaxy will reach the speed of light. And what that means is that even light cannot bridge the gap that is being opened between that galaxy and us. So there is no way for extraterrestrials on that galaxy to communicate with us, to send any signal that will reach us once their galaxy is moving faster than light relative to us. And so that's an outcome of the accelerated expansion of the universe. All the galaxies that we currently see will eventually run away from us at a speed greater than the speed of light, and we won't be able to see their whereabouts after that time. And the more distant the galaxy is from us right now, the earlier this will happen. And in fact, all the galaxies above a redshift of 1.8 are already outside of our horizon. So if there is a cell phone out there trying to send us a signal, it wouldn't reach us anytime in the future. And the way to think of it is just like ants walking on the surface of a balloon. Imagine a person blowing up a balloon. The ants are moving on the surface at some speed. And you can think of these ants as analogs of photons, as radiation, particles of light moving in space. The photons have a finite speed, the speed of light, but space itself, which is represented here by the balloon, can in principle expand faster than photons propagate. And that's what happens in the accelerating universe. So these ants would visit only a small part of the surface of the balloon. They will not be able to communicate across large portions of the balloon if the balloon expands fast enough. And that's what happens in the accelerated expansion of space. The photons are unable to cover a region that is bigger than some scale. And in fact, if we look at the galaxies around us, out to a certain distance of, let's say, 300 million light years around us here in the upper left panel, there are a lot of galaxies within that distance right now. But once we wait a time that is roughly comparable to the present age of the universe, there would be fewer galaxies within that circle. And if we wait for 3 times the present age of the universe, even fewer galaxies. And eventually, if we wait 7 times the present age of the universe, we would only be able to see galaxies within this red circle here. So if we wait longer than 7 times the present age of the universe, eventually we will not have many galaxies left within our observable volume of the universe. And you might ask, how many galaxies do we expect to find within our horizon once the universe ages by a factor of 10, once it's 100 billion years old? And the answer is only one galaxy, our own galaxy. So, and this galaxy, by the way, will not be just the Milky Way. We see the Andromeda galaxy, as Bob Kirshner pointed out, approaching us, and it will actually reach us earlier. And so we, together with a postdoctoral fellow here, T.J. Cox, back in 2007, we did a numerical simulation of the collision between the Milky Way and Andromeda, trying to figure out what will happen as a result. And this is the only paper of mine that has a chance of being cited in 5 billion years. And here you can see the collision in terms of the gas and the stars that make up these galaxies. Eventually, the 2 galaxies will merge to form a big ball of stars and gas. These are called elliptical galaxies. We see a lot of them. And presumably, they resulted from the mergers of disk galaxies like the Milky Way and Andromeda. It's interesting to wonder what will happen to the sun. And here are a bunch of stars on a ring at the same distance as the sun is from the center of the Milky Way galaxy. And throughout the collision, these stars are being scattered. Within just a couple of billion years, the Andromeda galaxy will come very close to the Milky Way. That's the first passage. And in fact, right now, Andromeda is very small, as you saw on the photographic plate that Bob Kirshner was showing us from Hubble's data. But if you wait 2 billion years, the Andromeda galaxy will just looming over our horizon, will be as big as almost the entire sky, as big as the Milky Way. But the 2 galaxies will not merge at that time. And in fact, it's possible that the sun will be carried away with the Andromeda galaxy, so then we will see the Milky Way at a distance. That will be a beautiful sight. Eventually, the 2 galaxies will come together in a time that is shorter than the lifetime of the sun. So in fact, the sun would still shine at that time. And most of the stars that are currently at the same distance as the sun is from the center of the Milky Way will be scattered as a result of the merger to distances that are larger than the present distance of the sun from the center of the Milky Way by a factor of a few. So let me summarize the state of the universe. We cosmologists are exploring the scientific version of the story of Genesis, let there be light, and future observations that are using the biggest telescopes we can construct, and also the radio observatories that will go after the faint glow of the hydrogen in the universe. They will be able to unravel the details of how the first stars formed in the early universe. So you might summarize it in one sentence. Religious ideas, ideas that were previously in the realm of religious texts, are now being explored by science. And that's a very encouraging development. But if we think about the future, the situation is quite disturbing, because the merger product between the Milky Way and Andromeda, which I decided to call Milkomeda, will be the only galaxy in the distant future that will be observable to us. In the entire universe, we will be surrounded by vacuum in the standard cosmological model. And so eventually we will lose sight of the evidence we had for the Big Bang. And in that sense, we will have textbooks or books that tell us a story about how the universe started that we will be unable to validate, to check whether they are true or not. We won't be able to do the experiment that Bob Wilson was describing in the distant future. So the question is, will cosmology become a religion at that point? There will be a story being told without us being able to verify whether it's correct or not. We will have to believe in it. So there is some regression in the distant future that we should expect. And in fact, it's even worse than that, because once the universe will age by a factor of 100, the wavelength of the cosmic microwave background that is currently 2 millimeters, so it's that big, and that's how Bob Wilson was able to detect it with the Horn antenna, it will be stretched to be 10 to the 28 centimeters, as big as the horizon of our observable universe. And so there will be no sense of an electromagnetic radiation to assign to this entity. The cosmic microwave background will not be measurable, even in principle, irrespective of how advanced the technology would be. You won't be able to detect an electromagnetic wave associated with the cosmic microwave background because its wavelength would be as big as the universe. And there will be no trace of the Big Bang, except that we actually had a snowstorm a couple of years ago where Harvard was shut down, and I was worried about this future, and it really bothered me that we won't have any evidence to the fact that the universe is expanding. We'll have only our own galaxy surrounded by vacuum. Is that really the case? And then I realized that, well, it's not exactly true, because our galaxy is spitting out stars continuously. And these stars are coming from the center of the Milky Way galaxy due to the interaction with the black hole at the center of the Milky Way. These are called hypervelocity stars, and are being ejected once per 100,000 years from the center of the Milky Way galaxy. And what would happen to these stars is that once they escape from our galaxy, they will be carried away by the cosmic expansion. So these stars could serve just like the galaxies that Edwin Hubble was looking at. You can see how they recede away from the Milky Way galaxy, and you can see their accelerated expansion. So you can use them as tracers of the cosmic expansion, and then you can try and figure out what really happened when Milkomeda was made, a long time before that time. And one can, in principle, figure out the conditions in the universe at those early times just from the properties of the Milkomeda galaxy and the fact that those stars are running away, telling us what the mean density of the vacuum is. So that is actually a very interesting thought, in the sense that 1 trillion years from now, it will still be possible to validate cosmology textbooks by watching these stars running away from the Milky Way galaxy. And of course, close to the center of the Milky Way, it's the gravity of the Milky Way that matters, but once these stars escape, the cosmic acceleration takes over and allows us to figure out that there was actually a Big Bang to start with. Thank you.